Okay, since our overall significance level increases with each new comparison that we have to make, then we need some way to counteract that and keep it from our overall significance from getting out of control. So what we've got is the Bonferroni correction method. And in that, what we'll do is we'll use a smaller significance level for each of the individual tests in order to kind of keep that overall significance manageable. So what that says is if you want an overall significance level of alpha and you're doing M comparisons, then you should do each individual comparison with a significance level of alpha over M. Then the overall significance will be alpha or smaller. We do need one more formula in order to figure all of this out, which is how do we know how many comparisons we're making? So it says if K is the number of groups that you're comparing, and you want to figure out how many comparisons, M, do we have to make, then you can do K times K minus 1 over 2. Okay, let's put all of this into practice. So we have biologists collecting data on the health of sea lions living in 4 distinct regions of off of the northern Pacific coast. They took measurements that reflected the overall health of the sea lion colonies in those regions, and they wished to test the hypothesis that the mean health, so again we're still talking about means, is the same for each region. So if they choose to do the t-tests comparing each region to every other region, how many comparisons must they make? So first we need to put this formula that's still showing here into play. So how many comparisons? They have 4 different groups. So it'll be 4 times 4 minus 1 over 2, or 4 times 3 over 2, 12 over 2, which is 6. So they're going to have to run 6 different t-tests in order to compare 4 groups together. Okay, so if they want to have an overall significance level of 0.05, we want to apply this Bonferroni correction to determine what significance level should they use for each of the individual t-tests. So that is the alpha over M formula. We want the overall significance level to be still 0.05, but we're making 6 comparisons. And if you divide that out, what that means is they have to set each one of their individual tests to an alpha value of 0.0083. So think about how that will drastically change the kind of results that you get. If your alpha value is that small, it means you will only reject your hypothesis if if the value you get for P is smaller than this, then you're very unlikely to reject it. You have to get a very, very small p-value. So it definitely changes how the testing works, but it's the only way that we can really counteract, again, that overall significance from getting out of control. Now, when we're examining several groups, we can also create confidence intervals for each group, but the same problem occurs. It says if we construct a 95% confidence interval for each pair, then there's a 5% chance that any individual interval does not include the true difference in the means. And thus there's an even larger chance that at least one of the intervals does not include the true difference of the means. So you run into the same problem here, basically, they're saying, when you try to do confidence intervals. So we can apply the Bonferroni correction again, and it says if you want an overall confidence level of L, then you have to make each individual confidence interval with the level 1 minus this alpha over M value multiplied by 100%. Now that looks really confusing. It looks like it's a lot of work, but our hypothesis alpha values and our confidence interval confidence levels have always been related in the same way. If I want to make a 95% confidence interval, then that's the same thing as having an alpha of 0.05. So you can see how 95% and 5% are related. They're just the complements of each other. So this formula right here is nothing new, All it's saying is use the complement level. So it says if we wanted an overall confidence level of 95% for this same sea lion example, what should the confidence level be for each of the individual intervals? So using this formula, what that's saying is take 1 minus, this value is what we just got up here, that's the same. So 1 minus 0.0083 and turn that into a percentage. That's all that means. So I find the complement, so subtracting that I get 0.9917, and changing that into its percent form I get 99.17%. So these are related in the same way that they've always been. So a 99.17% confidence level is the same as a alpha value of 0.0083. It's just we're talking about the two different tests. If you see the word simultaneous confidence interval, all that's meaning is the individual confidence intervals that you would be creating. And so when we use this Bonferroni correction, we produce a collection of simultaneous confidence intervals so that we can be 95% confident that all of them include the true population parameter. So again, we want to mitigate that possibility that one of them misses. In order to have that overall confidence, we have to make sure that all of them actually hit the value that we're looking for. What we're going to see in the next few sections in chapter 11 is that this is the hardest way to do it. It takes a lot of brute force, they're long, and we really aren't going to dive into it any deeper than what we just did. We're going to look at an alternative test that we can instead run that makes it so that we don't have to do all of these different confidence intervals.